We left off in the previous class at the point where we had discussed what is impulse. That is, when a force is applied for a period of time on an object, we call the product of the force and time as impulse. And it is obvious that an impulse creates a change in momentum. Now the amount of change in momentum depends upon the force and the time for which you apply a force. So if you take a same amount of force and you apply it for a shorter duration, you will get a certain momentum change. If you apply the same force for a larger duration of time, then there will be a greater change in momentum. So we can see that there is a connection between impulse and momentum, but how they connect, that is not clear yet. So I'm going to approach that question from an entirely different perspective. So the situation that we create is that there is a sort of a 6-foot cupboard, a tall cupboard or a structure, and you are made to stand on top of that structure and you are asked to jump down. Okay. So now the thing is that many of you may realize that this can be quite painful when you jump down from the cupboard onto the hard floor. You remember what our floor is like, right? It's tiled, hard stone floor.
Yeah.
If you jump down on it, it is obviously going to pain. And some of you might say that I wouldn't jump if you asked me to do it. Some of you might be more ready to try it out. But let us say that you are asked to do this, and I give you 3 surfaces which are possible for you to jump on. Okay, and the choice is entirely yours. So what are the surfaces? The first surface, let's call it the situation A, is when you land on a hard floor. Okay, like the floor that we have in the classroom. And so here is your feet. Just as it's, okay, it hasn't swollen up yet. It might get swollen up later, but not yet. Okay, and it's moving obviously with a certain speed. So when you have something like 6 feet, you are coming down with what kind of a velocity? Give you some velocity. What do you think in terms of meters per second? How much velocity can I give it? Shall I say 5 meters per second?
Yeah.
Okay.
Yeah.
5 meters per second sounds reasonable for a height like this. Okay. And let us say your mass is average weight of a student in class 8.
40.
I'll put it as 40 kilograms. Okay, so one choice is a hard wooden floor. Now, the next choice that I can give you is a floor which is made up of sand. Okay, so you have a sandy surface, like you know, in our long jump pit, what we have in our long jump pit, that kind of a surface. This one does not have enough.
A is wood, right?
Huh?
The surface A is wood, right?
Hard floor.
Oh,
Like the tile floor that we have in
Tile
school.
floor
okay.
that we have in our classroom.
Marble tiles.
Okay, so the next one is a sand floor or a sand landing area. And of course, the rest of the situation is exactly the same. And you're doing the same 5 meters per second and the same 40 kilograms. Okay. And the third one, the third type of surface that I'll give you is a cushioned surface, you know, foam surface, like the ones they use for pole vaulting in the Olympics, that kind of a surface. Okay. So that surface is soft foam.
Like our
Mattress.
mats we use for
Mattress.
PT, no?
Yeah, like the mats that we have.
But
So if
how
you have
thick
like
is
a
it?
multiple.
It's pretty thick. It's as thick as what is required for pole vaulters.
That's thick, okay.
That's thick. Okay. So and then you're landing on the floor. and obviously the same velocity and the same mass. Okay, so these three situations are there. This is situation B and it is situation C. Now I ask the question, which situation would you choose for minimum amount of pain? Okay, straightforward question. Situation A, B or C, which situation would you choose for the minimum amount of pain? You can answer the question in chat. So like expected, most students said C is the best choice in terms of avoiding pain. Some selected the B, but that was because they were not sure how deep or how soft the foam is. So I'm saying that soft foam, like like the sponge that you use in your house or the mattress that you have on your bed, except it's pretty thick. It can be like 4 feet thick or 5 feet thick. So several mattresses on top of each other. Then it becomes obvious that if you want to avoid pain, the best thing to do is select the softest possible one, which is situation C. Now, my question is, why? Why is it that the soft foam provides the least amount of force on the feet? Because if it pains, that means that there is more force, right? So if the least amount of force is applied on you, then obviously the pain, the pain will be lesser. So therefore, we select soft foam. But the question is, why is it that the soft foam is the choice of material to land upon? How do you answer that question? So Adira makes the point that the reason perhaps why the soft foam is the least painful is because it provides the most amount of time for the person to land. Okay, because in a hard floor, when you land on it, you immediately come to a halt. Sand floor takes a little bit more time, and the soft foam will obviously provide the greatest amount of time. So that is one observation that she makes. Now, any other observations? Okay, so you all can see intuitively that the best solution is the soft floor because there is least amount of force that is experienced in that. Perhaps that has got something to do with the time. It's obvious that the most amount of time is given for coming to a halt when the soft foam is used. So I want to throw something else into the equation now. Okay, I say that let us think as physics students, as students of physics, thinking in terms of what happens when you land. Okay, and let's examine the first situation for that. So when you land on a hard floor, your velocity comes down to zero. Okay, so that's the point, right? When you hit the floor, what happens is that your velocity comes down to zero, and there is obviously a force that acts on you in order to do that. Okay, now what is the change in the velocity that is taking place? So I'm looking at the change in the velocity. Rather, let me just say change in momentum. So what is the change in momentum that is taking when somebody lands on the floor when you're jumping from the cupboard? So you can say that it should be the final momentum minus the initial momentum. Okay, that's what happens when you land on the floor, when you come to a halt, right? Your momentum goes from a value that is there to a value after the impact. Did you understand this point? P2 minus P1?
Yeah.
Yeah?
Yeah, sir.
Yeah, I'm just saying a point. There's nothing to be understood at this point of time. I'm just putting something more into the whole question. So I say that the final momentum is mass times the final velocity. Okay, and that minus the mass times initial velocity.
Yeah.
That is going to be your change in momentum. What is the final velocity after you have landed on the floor?
Zero.
Zero.
The momentum is zero.
Zero.
Right, very good. So m times 0 is the final momentum, and your initial momentum according to this value is 40 times
Zero.
5. That's your initial velocity.
The momentum is zero. Yeah.
Yeah. So 0 minus 5 8s, 5 4s are 20, 200. Okay, so your momentum change, so delta P equals minus 200 kg meters per second. The minus just indicates that it is reducing, nothing else. Okay, so don't worry about that. So there is a momentum change of 200 kg meters per second. Are you all on board with this? Are you able to follow this?
Yes, sir.
Yes.
Yeah.
If anybody
Yes,
didn't
sir.
get it, ask now.
Okay, sir.
Got
I
it?
didn't get it. I didn't get it.
Vashisht, I'm just saying that the momentum change, I'm throwing something into the mix. I'm saying that let us look at momentum change because we are students of physics and we are studying momentum. So when you land on anything, okay, whatever be it, the momentum change, if you look at it, it will be final momentum minus initial momentum. By definition, momentum change has to be final minus initial. Final momentum is m times say Vf minus initial momentum is m times V. Final velocity in all three cases is going to be 0. Your body is going to come to rest. So therefore the velocity turns to 0. Right? So final velocity is m multiplied by 0. If you want, I can write it as 40 multiplied by 0 because the mass of the person remains the same unless you break a leg or something. Minus mass multiplied by the initial velocity, which we said was 5 meters per second. That we just took it as a number. So if you do the math, then the change in momentum comes out as 200 kg meters per second. So is it clear now, or would you like me to explain it again?
Yeah,
Yes, sir.
I understand.
You got it. Why I am saying this? Okay, that this is the important part. The change in momentum, is it different for the situations A, B, and C?
No.
No, it isn't, right? In all three cases, the object, that is you, are going to come to rest. So therefore, the change in momentum as given by the situation is always going to be 200 kg meters per second. Okay.
Yeah, sir.
So can you say that the force is produced by the change in momentum?
What?
Huh?
Can you please repeat
Could you
that?
repeat?
Yeah. So I'm saying that you can see that the change in momentum in every case is 200 kg meters per second. Agreed. Okay. Now I ask you, but there is a force that is different in all three cases. Like say, for example, if I had to illustrate it, I would say that, and you people would agree to this, that the force is the greatest in this case, the force in situation A, is lesser in this case, force in B, and is the least in this case, force in C. You agree? We all agreed to that already.
Yeah.
Right? By making a choice of C, you have already agreed to that. So now we are trying to understand, where does this force come from? Does this force come from the change in momentum? Can that be a rational argument?
It
No.
comes from this. It's the support force from the
It is a
floor.
support force from the ground, but is it because of the change in momentum? That's what I'm asking you.
So you're
I don't
saying
think
that
so.
Shouldn't be, right?
You're
So
saying
the support force is basically the amount of force you apply to the ground, no?
Yeah, it's exactly the same. You apply to the ground the
Yeah.
force that the ground also applies on you. But I'm asking,
But
can that force, can the differences in the forces be understood as a result of the change in momentum? In all three cases, the momentum change is exactly the same.
and if the force I'm applying to the ground is the same,
Yeah.
the reaction force should also be the same. So it's not.
So what are you saying therefore? Is momentum the reason? Change in momentum the reason?
It's not caused by that.
It is not caused by that.
Change in momentum is the same in all three cases, right?
Exactly. So
Yeah,
since
sir.
the change in momentum is exactly the same in all three cases, the force cannot be produced by the change in momentum. Okay.
Yeah,
So
exactly.
it looks like we have come to a dead end. If the change in momentum is not the one that is producing the force, then what is producing the force? We have to go back to our intuition. What did our intuition tell us? Just a moment, Rohani. Our intuition and Adira and others who agreed to her said that the time seems to be the factor over here. The amount of time required in the soft form for doing the same change in momentum is more than the amount of time that is obtained by the hard floor. So we can ask the question,
Or the
how
sand.
much time does it take to come to rest in a hard floor in comparison to the time taken for the soft foam to do the same thing? And we have to investigate that next. Yes, Ruhani, your question.
Yeah, sir. So are you saying that the change in momentum is out of the picture here?
It is not out of the picture, but it alone cannot explain the fact that the forces come out differently in all three cases.
Okay, so it's not the reason forces come out.
It's not the reason. We have to look at the next culprit, which is time. Okay. So what about time? Time in situation A, time in situation B, and time in situation C. First of all, are they the same?
No.
No.
What time? The time required to bring the momentum from something to zero. That time we are talking about.
So
Yeah.
A, B, C are in like ascending order.
A, B, C are in ascending order. So
Yep.
I'm just again going to throw some numbers into this for the heck of it. I say that it's a very hard floor. So the amount of time that it is going to take for the body to come to rest is about 1,000th of a second. Okay.
Okay.
Just for the heck of it, I'm going to say that. Yeah. Tell me. You agree with this?
Yeah, okay.
Yeah. Yep.
Okay, I mean, agree with the cells. What can you say? I'm just throwing some numbers in. So the time required for the same thing to happen is 0.01 second, 1/100th of a second. Okay, and for the soft foam to do that same task, I say it is 0.1 second, 1/10th of a second. So you may or may not agree with this, but I'm just throwing some numbers into it for the heck of it. Okay. Now, what we can do, now that we know the time intervals that are involved over here, we can work out what is the rate at which the momentum goes down. Okay, so the rate at which I'm going to erase this section of it so that I can write the calculations near them. The rate at which the momentum goes down, I would say, is change in momentum, or delta P, divided by the time required for the change in momentum. Are you able to appreciate this?
Yeah, that's right.
Could you repeat?
So I'm saying that momentum is coming down from 200 to 0. The time that is required for the momentum to come out is different in each cases. So I'm going to find out the rate at which the momentum comes down. How fast does the momentum come down?
The rate of the change of the
Rate
momentum.
of the change of the momentum, exactly, the first derivative. Brilliant. Okay, so if you got that point, then you will appreciate what I'm going to do next. So I look at situation A, okay, and in situation A, the rate of change of momentum is, for the purpose of calculation, I'm going to leave out the minus sign that we got there, 200 divided by 0.001 seconds. For
200,000.
situation B, I'll put situation B over here. It will be the same 200, because the momentum change is the same in all three cases, divided by 0.01. And for the last case, situation C, it will be maybe I should write it a little bit higher so it comes on the screen. I can write for situation C, it will be 200 divided by 0.1. Now, what are the answers to this? What are the answers to this?
200,000.
2 lakh, yeah.
200,000. What we don't know, we'll keep it there. What is the answer to this? 20,000. Am I right?
Yeah.
Yeah.
Could it
Yeah.
be kg meters per second square?
Yes, you are absolutely right. It's kg meters per second square. And what is kg meters per second square?
I don't know the name.
Momentum.
Momentum.
No, you're on
Rate at which momentum
It's
changes.
the acceleration.
kg meters per second square. Meters per second square is acceleration. Kg is mass.
Yeah.
So what have you
Oh.
got when you multiply mass and
Force.
acceleration?
Force.
Force.
MA.
Wow.
You got
Oh my god.
So what is the unit for this?
Newtons.
Newton.
Oh,
That is so cool.
Sir, now we can find the impulse.
You have found the impulse already.
Impulse will be same, right, in all.
No, impulse will not be
No.
same because the time is different, right?
But
Oh,
the
yeah,
force
yeah.
is also different.
Force
Right?
was also
No,
different.
you're right. Impulse will be the same, but we'll come to that. Okay, we'll come to that. Just hold on. So what have we found out over here? We have found out that when you find the rate of change of the momentum, what you get is a force. And what is that force? That force is this force.
Oh.
It's 200,000 in this case.
Oh.
It's 20,000 in this case, and it is 2,000 in this case. Okay. Now the force may seem like an enormous amount of force, but just think about it. The amount of weight that lands on your ankles, your ankle bone and your knee bone and your hip joint and all that, the force that is applicable on it is 200,000 newtons, but for a very short period of time. Okay, so the question is that, is this going to break your bones? How do you figure that out? You try to work it out in terms of your own weight. So
Or you can jump off and try it on.
if you're 40 kilos, okay, if you're 40 kilos, this is a little bit extra. If people don't get it, it's perfectly all right. So I'm saying if your weight is 40 kilo, if your weight is, your mass is 40 kilos, then your weight is 40 times 10, 400 newtons.
400.
Okay, so what is the ratio of this 200,000 to your weight, 400? It is approximately 500, am I right?
Yeah.
Yeah. So what is happening is when you land on the floor by jumping from a high point and your initial velocity is 5 meters per second, your mass is 40 kilograms, and the impact time is 0.001 seconds, then your body has to bear 500 times your own body weight. Okay, which quite likely means that you're going to break some bones.
Yeah.
Okay,
At least
so
your ankle you're gonna break.
yeah, so in this situation you are going to land up in the hospital. You'll have to go for an emergency trip to Sancheti.
Unless you bend your knee, sir.
Unless you learned how to do it right, so you absorb the impact by actually bending your knee and rolling, which will increase this. You see?
Yeah. Time.
Yeah, so the force will decrease.
So yeah, so the force will decrease. Okay.
Sir.
Let's look at this situation. Let me just finish this, then we'll take the questions because we are running out of time. Let's take this situation now. In this situation, 20,000 newtons. So if 200,000 newtons means 500 times,
2000.
in this case, it will be 50 times your body weight, 50x your body weight. That kind of force your body can easily absorb. So your knee joints, the tendons, the ligaments, these will work together to reduce that impact, and therefore your bones are likely to be spared. Okay, so 50 to 100 times of the body weight our joints can take for a very short period of time. And obviously then the softest landing happens in this case, where the amount of force experience will be only 5 times your own body weight, which is very, very easy. Even a child can do it. If you drop a child also onto a soft foam with those kinds of impact times, then nothing is going to happen. In fact, you might even have some fun. So therefore, in conclusion, we can say that rate of change of momentum is force. And I will illustrate that in a moment. If you have any questions, you can ask now. So if you followed all the arguments, what we arrived at was the force is equal to change in momentum divided by the time taken. Correct?
Yes.
We arrived at that.
Yeah.
Look at this. F times t is equal to delta mv. Now do you recognize what is the connection between impulse and change in momentum?
Yeah, they're equal.
Yeah.
So
Duty.
the time will go
Yeah,
and like the time will get divided over there.
Exactly.
Hmm.
So it's just a different form of the same equation. you can always write it as F times t equals delta mv. So
Yes, yeah.
impulse is change in momentum.
Sir,
But the most interesting result, let me just finish this last point, but the most interesting result is this. Okay, and this has a lot of implications in terms of sports, in terms of ballistics, and those implications we will explore in the next class.